Yeah, it started now. Recording. Yes, so electronic conduction involves motion of charges. That is, we have discussed, and we have also discussed this Drude model. First, how to visualize the current density, that is total charge divided by area divided by time over time delta t, right? So this is a very simple case. So we have discussed, and if you look at the v dx, that's the average velocity. It's moving in a particular direction, and this is what is shown. And then circle 1 is nothing but your electrons. Okay, so can you see this marking that I am doing? Red marking?
Yes, sir. Yes, sir.
Yes. So I'm using pen. So this is what is, and it's already discussed other day. So then I told this, it's not only one electron, you have number of electrons, so n number of electrons. So n is nothing but, it depends on per unit volume. Say if you take 1 meter cube volume, 10 to the power 28 number of charge carriers will be there. Okay, average 10 to the power of 28 number, depending on doping level and other things. It may increase or decrease, whatever, but on average this is. So if you take total number per unit volume, and that means total number is n and total volume is v, so you have small n is equal to capital N divided by v. Okay, so this is what is known. And now you have one electron, so that is Vx1, then Vx2, Vx3, then you have Vxn. You have the average velocity is nothing but 1 upon n into all the summation. So that means it's not only one electron, we have to take the average of many electrons and then sum them up and take the number divided by the total number. So you get the average this. So when you do all those things, so you get a very simple relationship in terms of velocity, that is delta x is, that v dx into delta t, because v dx is nothing but delta x by delta t into delta t is equal to delta x, right? So once you know delta x, you can also know what will be the volume. So delta x into A is the volume, and E is the electronic charge, and N is the number per unit volume. So in unit volume, so number of electrons is this much, n into this, and so therefore the total charge will be ENA delta x. Now that will be Q, you understand? So that will be Q. If you take this and go ahead, this thing, charge divided by area divided by time, you get the current density, Jx, and finally Jx is equal to EnV dx. So yesterday also I told, and I am repeating. So, but what is interesting here, the electric field is not a stationary field. If it is a time dependent or AC field, then what happens that with time the amplitude changes. So therefore you have to express Ex in terms of as a function of t. If you express as a function of t, so therefore velocity is also dependent as a function of t, v dx. So therefore current density is also function of t. So the earlier slide was independent of t. Now you are introducing time dependent part, and which is a realistic concept, because we always talk of AC current, AC electric field like this, alternating sort of thing. So it's a time variation, so that you could realize that it is nothing. So you have to give a function of t, that's all. And suitable function, sinusoidal or square wave, whatever function you need to assign, and you get the result, right? So therefore we must examine the effect of electric field on the motion of electron in the conductor in terms of the electric field when it is dependent on time. And to demonstrate that, if you find in literature that it's a very simple to take a copper crystal or say kind of a metallic crystal or FCC crystal, this, and try to work it out. You understand? Because when you talk of electrons, where these atoms with respect to a particular material, and this material as an example you have taken copper. You understand? So if you take copper, which is an FCC, and FCC means 4 effective number of atoms are there per unit cell, and what is the valence electrons, all those things. If you take those simple things and then if you work it out, you find this. So what happens, this 4s cell, this electron is a valence electron. It is contributed by each copper atom. Now there are millions of copper atoms, so therefore millions of electrons are there, and those electrons will be in a common place or in a common sharing spaces. It will not be sticking to a particular atom. It as if it will be belong to all the atoms, right? So therefore we talk these electrons are nothing but conduction electron, because they are free to move. It is not a semiconductor type. They are free to move in the metallic case. You understand? Semiconductor, it has got a band gap, then it has to be in the conduction band. So those things are not there. So it is to move. So if this thing happens, then what will happen? That these copper ions, electron is moving, and copper, say the plus lattice points are there, I mean those charges are there at the respective lattice point. So there will be an interaction between the electron negative charge and the positive charge of copper. So you have a attractive interaction, you may have the repulsive interaction also, because electron will get away. So there will be, this lot of push and pull. This thing will happen while the conduction electrons are in motion. You understand? So electrostatic attraction will be there. And this electrostatic attraction, I have mentioned this, and that will give rise to kind of a potential energy and kinetic energy. You understand? And now if you compare this as an analogous situation to motion of gas molecule of the gas phase, the kinetic energy of the gas atom from your first fundamentals is 3/2 kT. You understand? K is the Boltzmann constant and T is the temperature in absolute degree. So 3/2 kT is the average kinetic energy of gas atom. You understand? In the gaseous state. But how it is different from, although we may treat this as a gas atom, but how it is different from gas atom is, so there is nothing like a attractive and the repulsive forces. Those gas particles are not your positive or the negative charge particle, they are all neutral particle. Now here in the electron, they have to undergo electrostatic attraction, electrostatic repulsion. So therefore, you cannot govern this gaseous theory or the gas molecular theory into this electron or this positive interaction case. You understand that what is the critical difference? You understand, I believe. Otherwise, you say electron gas. Electron gas, by saying it's fine. Saying it is fine, electron gas. But if you treat it, it cannot be 3/2 kT. It will be something else. So that we have to realize, we have to understand. Because these are all very fundamentals. You need to understand. These electrons strongly interact with the metal ions and with each other as a result of electrostatic interaction. Is it clear? Up to this point is clear? Yes?
Yes, sir.
Yes, sir.
Absolutely.
Yes, sir.
Now this is what is pictorially or schematically shown. You have the bigger circles, empty circles are nothing but the lattice points, that means the copper positive ion, right? Now because of finite thermal, finite temperature, is not a 0 degree Kelvin, it is above that, so therefore it has got a vibration. So this vibration is shown here. This is what is shown here. I mean, this way is shown here, and this is shown any random kind of the vibration. And the free electron is also moving in this direction, and then from here in a very zigzag fashion, it makes its way, to pass through in between. Whenever it comes across the vibrating atom or this ion, so it collides and it gets diverted. So it is not moving in the direction, in this direction. It was supposed to move in this direction. It was supposed to move in this direction. It was supposed to. This how it is happening. So it's all random. So therefore, if you look at the electron started moving with u velocity initially, and after a while it has come back to a position. So it is nearly in the same plane or the same position it is where from it has started its journey. So there is no physical movement of the charge. If there is no physical movement of the charge, you can say, you can consider, so it is nothing like a, you can say current has been produced, because current is nothing but you have to move, make this charge move in a particular direction by a finite distance. So it has not moved at all. So this is what is happening in the random situation or without application of electric field. Now when you apply electric field, say the situation is like this. If you connect two ends with a battery, so the positive is connected here and the negative is connected here. So the electron is negative charge, so it is directing to move in this, it is intending to move positive plate, but it comes across lot of the vibration, this thing collision due to the vibration of atoms. So therefore it got diverted here, it got diverted here, it got diverted here, but finally it has moved by a distance delta x. So this is what is interesting. So you get a final distance movement is nothing but delta x. So that delta x is not a zero. Delta x is non-zero. You understand? So this is what you should realize. So this is what is happening, and whenever this is happening, that means finite current is. So therefore, due to application of the electric field, so the electric field is in this direction, so you get this thing. So therefore, you understand, if you want to draw the current, you need to apply electric field. Otherwise, it's all random and there is no current, so it is what is written here. In general, the copper crystal will not be perfect. Now you come to further consideration that this is what is shown with respect to a perfect crystal. Perfect crystal in the sense all the atoms are there in all the assumed positions. All lattice points are perfectly filled, and there is no impurities, there is no second atoms of second entity. You understand? In copper there is no gold, say for example, impurity or aluminium impurity, only copper, so 100% pure. But because of the temperature, they are in the vibration state, right? No vacancy means no missing copper atoms are there. No dislocation means series of atoms, point defects. If you have a series of point defect, makes a line defect. So that kind of situation also not there. So it's an ideal or perfect crystal. You understand? Perfect crystal of atom. I hope you understand. Now when you talk of the real crystal or the the practical material, they all contain defects, the crystal defects, and these defects are nothing but vacancies, impurities, dislocations, maybe grain boundary, and many more things, surface and the same. And as a result, what will happen? They will contribute to nothing but a scattering. Scattering means if the electron is moving in the direction this, so here it will get scattered somewhere, it gets scattered here, it gets scattered here, finally it may reach. So this is all. So it will make it happen, this scattering, okay, these defects. More importantly, due to the thermal energy, the atoms will vibrate about their lattice site, what I have shown here with respect to equilibrium position. An electron will not be able to avoid collision with vibrating atom. It is bound to undergo the collision. Consequently, it will be scattered from one atom to another. In the absence of applied field, the path of the electron may be visualized, as I have shown this thing in the very first or second slide, where the scattering and this thing is. Anyway, so this is a very common concept. Basically, by this slide, what is introduced is effect of defects. You understand? The effect of vacancies, effects of dislocation, effect of impurities. And you have to live with it because these are the realistic or the real thing. So we have to derive expression by taking into account these effects. You understand? So we'll proceed, go along with this idea, right? When the electron reaches a crystal surface, it becomes reflected. I think this is what is explained here. Again, I have explained. So you can skip this. While reading, you can read this, right? So now, when a conductor is connected to a battery, I have already shown, you see, when a conductor is connected to a battery, electric field is applied to the crystal. As shown already, you have seen the figure. The electron experiences an acceleration. Because of the field, the force is nothing but E into Ex is the force. Whenever there is a force, you know the acceleration will be imparted and the electron will develop acceleration in the x direction to its random motion. So after some time, it will drift a finite distance in the x direction. Yesterday I told what is the meaning of drift. By applying electric field, it is the drifting. This effect is drifting the electron towards in the direction of the electric field, or rather it is the opposite direction of the electric field, whatever, depending on the sign of the charge. So this, and this is what is there, and what is the force applied is E into Ex, right? Now,
Sir,
yes, tell me.
Sir, earlier you said that electric field will be dependent on time, and from there we would find the current flow by putting it in terms of velocity as a function of time. Sir, I just wanted to ask, like, it is possible to get the potential energy and then calculate velocity if we know electric field as a function of x by doing minus dv by dx. But if it is dependent on time, then how are we supposed to find the potential energy and then go to velocity?
No, we can do that. So you don't have to go so much of complicacy. See, I understand. Yes, Paul Singh. Yes, I understand your concern. That's a very interesting idea you possess. But you just wait. It will not be that difficult. See, what happens when you talk of the potential energy, it is basically say distance related, isn't it? But when you talk of the kinetic energy, it is in terms of the velocity. Okay, velocity changes and those things are there. So, so what happens that if you apply the defects, or if you see the influence of the defects, how they govern the distance movement, that we have to see, and how they govern velocity change, that we have to see separately. And see, basically what happens, those particles possess the total energy, and this total energy is nothing but divided into kinetic plus potential energy. Now kinetic energy is coming from where? Basically it is deriving energy from the electric field. So electric field is a source. So that is why you consume power from the meter, okay, from your electric source, and you pay electric bill because you are consuming. Where that energy goes? Because it is converted into some other work. So this some other work is nothing but say making kinetic and the potential and the drifting and the drift mobility kind of thing. This is what is happening. Now these are the basic concept of movement of charge carrier in presence of electric field. But what you have pointed out, so it will come automatically in the system of derivation. You just hold on, you let it go for some time, then you will understand. Okay. Okay, Rahul, yes. So if you see what happens, that when you talk of the drift velocity, see the drift velocity is here nothing but Vdx, right? You express in terms of Vdx, and that is due to Ex. I told you whenever the drifting word is there, electric field is associated. Without electric field, there is no drifting phenomena, there is natural phenomena, right? So Ex is there. So you first consider the velocity Vxi of the ith electron in the x direction at time t is equal to say 0, or t is equal to t, or t is equal to ti. So what will happen, that there is one electron, like that there are several electrons. So I is a the I is a very generalized electron, ith electron. It can be nth electron and this thing. Now if you see that due to application of electric field, E into Ex is the force divided by mass, so you get acceleration into time, and that time is t minus, so the starting time is t, and ti is nothing but at that time where the collision has taken place. You understand? Till then it was freely accumulating or growing this acceleration, and the velocity is increasing. So therefore it is the t minus ti, that time is the important, not ti alone. You understand? At t is equal to 0 or t is equal to say t, after collision the journey has begun. Okay, then the next collision, successive collision is ti. In between it has moved freely, so that means it has got a freedom to develop acceleration, and because of the acceleration velocity has changed, and that velocity term got added into the initial velocity, and which was uxi, so therefore now the velocity is more. Now at t is equal to ti, since there was a collision, there will be velocity drop, again acceleration drop. Okay, so it will happen. So then what will happen at t is equal to ti plus 1 and this thing, and that too it is happening for all the electrons. If you take this thing phenomenon, you know, it's a kind of a very interactive system. If this thing happen, and then if you try to work it out, I'm just showing the basic principle. You can't individually take the electron and trace its path and calculate its acceleration and this thing. You have to go by certain mathematical methods, and that you have to tally with the experimental measurements. I am giving you the insight, then you realize actually what is happening in the system or solid state body, so that you can design the material by whatever suitable doping, selecting, number of electrons, valence electron mode, whatever this thing. So we'll slowly go into that. Now, however, this is only for the ith electron. So you need to work out for n number of electrons. Yes, I is equal to 1 to n. So that you have realized. So we assume immediately after collision with the vibrating atom, the electron may move in any random direction. So it is practically it was moving in this direction. Just after the collision, it may move in this direction, may move back in this direction, may go in this direction, whatever may happen. As a result, what will happen? If it moves in this direction, you would have got the 100% correct. Since it has got deviated, so if you take the component, theta component, so cos theta component, so it is always low. This contribution towards this thing is always low. So therefore, you see the current, loss of current is there because of the vibration. So therefore, a lot of superconducting and those idea, although it was a different thing, but idea has come. If there is no vibration, then the electron moves unhindered way. It smoothly it moves, and you get a very high conductivity kind of things. Okay. So this. So we assume that immediately after collision with the vibration, electron may move in random direction. That is, it can just as likely move along the negative or positive direction. This one. So you get, basically you have to take the average velocity, this average, and if you put the expression v dx expression from previous thing, so you get ex this thing and t, and this is electronic mass. And here instead of t minus, see earlier what we did, it is t minus ti for a t minus ti for ith electron. You understand? Ith electron. And when you take all electrons, n number of electrons, you have to take the average. This average is represented by t minus ti bar. Okay, so this is important bar you have. So you have taken that average time, free time of n collisions. Okay, so that is actually important. It is not a single, it is always bar. Suppose this tau is the mean free time, that is t minus ti bar, you represent is at tau, is the mean free time. or the mean time between two collisions. You understand? So therefore, for some electrons, T minus Ti will be greater than this. Some cases will be shorter than this. So if you take average, you get this. So finally, it is you express in terms of tau. This is the what you call the mean time or the mean free time. So you have the Vdx is equal to this. Why this? Because this is the constant of proportionality, and this constant of proportionality E tau by m is the electron mass, is equal to nothing, sorry, electron mass you are expressing in terms of mu d, okay, and this is nothing but a drift mobility. So Vdx is equal to mu d Ex, you understand, and mu d is nothing but E tau by m. So E is the electronic charge, m is the mass in terms of kg, in terms of gram, whatever, and tau is the time. So you can understand what will be the unit of mobility. Okay, this constant of proportion, this is called the drift mobility, mind it. So drift mobility is expressed this. I mean, this is the most important concept in solid state, that what will be the drift mobility, because that controls the electric current. Of course, there are other things also there, like charge carrier density and those things that we'll try to explore. What are the things? I hope you understand the meaning of drift mobility. Okay. So the equation relates the drift mobility of the electrons to their mean scattering time. This, why they relate? Because so drift mobility is connected to scattering time. So mean scattering time, or this thing, mean collision time, whatever. So there is a connectivity which is written here, and is directly related to the microscopic processes that cause the scattering of electron in the metal. You understand? That is where the material science or the materials technologist or you people like have to contribute. Since the drift mobility has got a connection with tau, and the tau is nothing but T minus Ti bar. So if T minus Ti is, say, instead of a 0.001 second, if you can make it 0.01 second, that means that tau is now 10 times more than this. When it will be 10 times more? When 10 times more means less number of collisions. You understand? So average movement of the electron without undergoing collision will be increased. So therefore time is increasing. You understand? Then this is possible only if you make a design a crystal which is imperfection free, impurity free, lattice vibration less, dislocation free. So who will do? It is the materials people will do when they grow the crystal, single crystals. We know how to grow the single crystal, perfect crystal, and if you do that, so therefore when you talk of semiconductor material, you cannot afford to have very low tau value. You understand that drift mobility is very high you want basically. So therefore if you talk of this, they are all single crystal based thing. They are not a polycrystalline material, because polycrystalline means lot of grain boundaries are there. So the grain boundary itself is a defect. So when the electron moves from, you understand the meaning of grain boundary. Huh? So this is where you have a strength. Suppose this is the grain, okay. So the electron moves from one grain. This is single crystal. One grain is single crystal. It moves to another grain. Then there is a scattering. So takes place. It deviates from here. Okay. So you cannot afford to have this. You have to have a single crystal. So that means electron is moving very smoothly. This one. So that is where the materials people will have to control during crystal growth, and to control, thereby controlling tau value, thereby controlling drift value, thereby controlling the conductivity value. You understand? So they are all interconnected, comes from the basic microstructure of the material. You understand? Single crystal microstructure and polycrystal microstructure, they are two different. So basically you are designing microstructure in order to design the conductivity value. You understand? So how you relate the morphology with the final property, and those final property will be seen by the market people. You see who are the user of the technology. not other people. They don't bother about what microstructure, but we know how to relate with the microstructure, because this is where you have a strength. Okay. From the expression of the drip velocity and the current density, this again you can relate this thing in terms of drip velocity, right? You get expression, and this term is called the sigma, and this sigma is nothing but conductivity. So the conductivity is finally multiplication of three terms. One is E, another is N. N is nothing but carrier density, charge carrier density. And carrier density, I told you, N is equal to, mind it, it's not a carrier. N is equal to N divided by V. So it is all the time density, carrier density, into mu D. And mu D is connected with whatever this thing expression we have derived. So it is related to tau and those things are there. So these three things collectively decide what will be conductivity. Now, instead of a single charge E, if you have a double charge, you will increase the conductivity by double the amount. Instead of a 10 to the power of 21 per meter cube to 10 to the power of 26 per meter cube carrier density, you will increase the charge by, say, so many times. If you increase the drip mobility from 1 unit to 2 unit, you will increase this thing. So it is all effect of multiplying factors, you know. Is it clear? Now here, until now, we have assumed that as if that drip mobility is independent. See, you have applied the electric field. You have a scope of applying electric field, a DC field, means a fixed field, or you can apply the sinusoidal field. Suppose you have applied a fixed field or DC field and you have derived the tau, and it is independent of field. Now drip mobility is important because it is widely used in as a electronic parameter or the electronic equipment, this device parameter, especially semiconductor devices. The drip mobility gauges how fast electrons will drift when driven by an electric field. So that is the physical significance, basically, how fast it is able to, for a given magnetic electric field in one material, how fast electron will be able to move in another material. Another material means in copper, how fast it is moving, in silver, how fast it is moving, molybdenum, how fast it is moving, for the same amount of electric field. In all three cases you have applied. You understand? So because it depends on material property, so that's what is stated. If the electron is not highly scattered, then the mean free time between successive collision will be long, tau will be large, and the drip mobility will also be large. That's what I told you. The electrons will therefore be highly mobile and be able to respond to the field. However, a large drip mobility does not necessarily imply high conductivity. Can anyone explain this corollary of this? It is very good that if you have a high drip mobility, because your expression says sigma is equal to E into N into mu, it will directly give high conductivity, but it does not necessarily mean the high conductivity. Who can explain this meaning? Any of you? Please tell me. Yes, Shivam Yadav, are you there?
Yes, sir. Yes, sir.
What do you understand? That high drip mobility does not necessarily mean, it means high conductivity, but not necessarily means it is not the only condition. So that's what his statement is.
Sir, because concentration of electrons is also the factor, you know.
Yes, excellent. Very good, very good. This is what is not only concentration, even the charge also. You see, E means one electronic charge. You may have, say, double charge. So double charge, say, beryllium kind of thing, okay, kind of thing, or you may have the, you may say sort of the polyhedra sort of thing, okay, polyanionic system kind of thing, or say transition metal, which may have a higher oxidation state and those things. So this kind of thing can be possible that if you substitute, say for example, lithium is a 1+ charge. Instead of lithium, suppose if I put double charge, you understand, kind of a, think of a situation, double charge. Say the sodium chloride, sodium is a single charge. If I use, say, double charge kind of thing, so that will give you better conductivity. Okay, what you address, this is this sounds perfect, and we should realize. Okay, so then I believe you have understood until this type, until this term. Now see, the mean time between collision tau has further significance. And now actually why tau we are stressing more is because tau decides many things. You see, basically tau relates the scattering probability, tau relates the time of flight. So therefore, if tau is more, that means you have the higher drift mobility. Now, so that means 1/tau will give you the collision probability basically. So the mean frequency of collision or scattering events. I hope it's very simple. If tau is this, 1/this will give you how many scattering will take place per unit time kind of thing. So this is how we'll give you. So the mean probability per unit time of the electron will be scattered. Okay, you are saying same thing in different form, so that just to realize more and more. So therefore, over a small time, say delta t, so the probability of scattering will be delta t by tau. So the probability of scattering per unit time is a time independent and depends only on the nature of the electron scattering mechanism. You understand? You have to realize two things here. I said just one slide before that now the effect of time variation of the electric field has not been taken into consideration when we talk of tau at this point of time. But we have already explained the effect of field, effect of time on electric field, so that will give you the variations and all this. Now we will introduce with respect to time variation, how the tau also will change and those things we will introduce. So until now it is only the electron scattering mechanism. See, there are many scattering mechanisms, you know, Rayleigh scattering, coherent scattering is there, incoherent scattering is there, depending on this thing. So just to realize that we have this, then we will add the time dependent part. This is one important assumption in the derivation of the drift velocity Vdx. We obtain Vdx by averaging velocities over this in the equation. The drift velocity therefore represents the average velocity of all electron in one instant, and Vdx is the number of this thing and this. Anyway, so this is all we have already explained. So after a time interval delta t is this, an electron would have been displaced by a net distance this along this. You understand? So when you talk delta t is greater than tau, that means if delta t time is greater than tau, that means it would have undergone a collision because it is above tau. So this is how you can calculate. Anyway, let us not bother much about this thing. I hope fundamental part you have understood, and this also says the one on the same thing. Now two velocities are the same only under steady state conditions, and this. Why two velocities? This is what is written. If you talk of the directions and all, so you will be able to realize this what is written there. Let us see. Now you see basic definition of the drift mobility. Again I place here mu d is equal to this. Suppose that the mean speed of the electrons, not the drift, mind it, not the drift, is u. U is the mean speed of the electron. Electron is moving in a natural way because of its movement. Okay. Then an electron moves a distance. Moves a distance L is equal to u into tau is the total distance in the mean free time, which is called the mean free path. You understand? Mean free path. The drift mobility and the conductivity becomes this. Now you can express in terms of, earlier it was E tau by me. E tau by me from there. So you replace tau is equal to what? Tau is equal to L over U. Okay, so L over U if you put here, so you are introducing mean free path into the drift mobility. You understand? Now why you have introduced mean free path? To avoid the mean free time or the relaxation time. So that has got a meaning. You will realize this thing, consequence of it little later. Once you have this, so again this fundamental equation you put and you get, that means basically it is you see, basically it is E squared, because 2 square NL divided by MEU. I hope this is simple exercise, that's all. Now in this equation what you have done, you tried to replace the mean free time tau by mean free path. You understand? Mean free path. So there, is it clear? Can you respond?
Yes, sir. Yes, sir.
Okay. So simply there the equation you are deriving one after other, that's all. Why you are deriving? Because it has got a meaning. In some place you will find the data will be given in terms of mean free path. In some place you will find data will be available in terms of mean free time. So therefore you should be able to handle both these things depending on situation. So that's all. It is assumed that after each collision the velocity is randomized. So this is, you have already realized. The scattering process, what are the scattering? Lattice scattering is able to randomize the velocity in one single scattering. In general, not all electron scattering processes can randomize the velocity in one scattering process. If it takes more than one collision to randomize the velocity, then the electron is able to carry with it the some velocity gain from the previous collision and hence possesses a higher drift velocity. Okay, so that means we are trying to go little intricacy into the problem, that due to scattering, if randomization has not taken place, okay, then what will happen? Whatever the build-up velocity was there, it will carry for some time until it gets randomized in the next successive collision. If it is randomized in the first collision itself, then it will lose velocity. You understand? And then, so therefore everything is now, you know, the average behavior and the different ways of expressing how the higher drift mobility for some electrons will be there as compared to other electrons. So these are the understanding you can realize from this lecture. In such cases, one needs to consider the effective mean free path. A carrier has to move to eventually randomize the velocity gain. Okay, so whatever I say. So with that, the first part of this thing, your classical theory part is good enough. If you can realize up to this is good enough to take up the next part. Now tell me if you have any question. Any of you has any question? Yes, Akanksha?
Yes, sir.
Yes. Tell me what you have understood from this lecture, very briefly, in 2 or 3, 1 or 2 sentences. Can you express what essentially we have discussed today? Tell me something at least that yes, we have discussed this part. You are there, na, in the class?
Yes, sir.
You are attending?
Yes, sir.
I see your presence. You are there. But point is there are two things. Once you are connected and you are not present, okay. Second is you are connected, you are present throughout. So there are two things that we have established in the class, because we cannot see you. Neither your video is on all the time. So we have to believe that you are all present while you are connected. But it is absolutely up to you what you do. Whether you are present or you are doing parallel work while connecting yourself, do not know. We have no control. That is our shortcoming of this system, online class system. If you turn on your video, what will happen? Bandwidth problem will create this. Neither you will be able to see properly, not speak properly. So therefore we suggest that okay, you keep your video off while keep your audio only on. Now I want that whether you have, if you have attended, tell me in one or two sentences that what essentially we have discussed today.
So like mean free path, the drift mobility and relaxation time.
Yeah, mean free path of what? Whose mean free path?
Of the carrier.
Which carrier? So there
So
are
like electron.
Yes, electron. Say this. We are mostly talking in terms of carrier means electron, not the positive charge carrier like sodium, lithium, not the negative charge carrier like chlorine, say bromine or fluorine kind of things. We are talking of electron. So you should say specifically this shows that you are attentive. So this shows. And okay, mobility. How do you define mobility? As yesterday also I have defined mobility. So how do you define mobility? What is the definition of mobility?
So like the ability of it to move. I am.
What is that? Tell me again.
So like the ability of the electron to move with the electric field. Like it is the velocity divided by the electric field.
Velocity per unit electric field. Good. So ability of electron, it is basically the influence of electric field on the velocity gain, isn't it? Or the velocity. So this is what is the mobility. Okay, that's fine. Ratnesh, Ratnesh Kumar Verma. You're not there? Your where is Agampreet? This class senior, is it there today?
Yeah.
Is it there attending? I don't think he is there. See what happens, I tell you, your group wise list I did not get from the academic section. You have 4 groups, R1, R2, R3, R4.
Yes.
So therefore I could not make your tutorial group and so send you the link, because that will be a separate link group wise to hold tutorial class. Like yesterday there was a tutorial class with I think R3 group, and then today with R4, R2.
Yes, sir. R1 and R2.
Yeah.
Yes.
But I asked for that from the academic section. They told that it will be provided in due course of time. I don't know why it is so. So if you have already group wise this your list where I have emails and everything, so you can send me so that I form group and send it. At least from the next Monday we can start the tutorial. Because
Yes, sir, I will share.
Yes, sir.
For R1 I will share.
Nick, can you share? Can you
For
send me a complete
Uh,
one?
complete. Okay. The batch representative will coordinate you, sir, for the
Yeah,
R1, R2, R3, and R4.
exactly. If you tell
yes,
me
sir.
the
Every batch representative will make a separate group for you and coordinate accordingly.
okay, or you can send four of you will be sending four R1, R2, R3. So accordingly, I will make a group email
Yes,
sub batch wise and send you okay the link. So you have to
yes,
again register with the team code and then join this thing. So that from the next Monday we should be able to start the tutorial class. I do
yes.
not know why this they are not ready. Academic section is ready this time. And you said that you have not got also your grade card, no, so far? Or you
Yes, sir.
got?
It's no, sir.
No, sir.
Okay, I don't know what is the reason. Yes,
Yes,
anyway.
sir. It's kind of late.
Anyway, so I think if you all have understood what you have said, what I have said, I can stop now and I'll fix the next class. I'll send you the link. Okay, so I'll wait for your this thing, sub batch email ID. You email me to my email address, right?
Yes, sir.
And
Sir,
this lecture I'll be uploading today. Okay.
sir, what where you will share the slides?
Yeah, I'll just okay. You can see that there's a file upload file section. If you go to class material and then you will see the slides. I think there is option you
Okay.
go to class material and there I will upload the file and you can download it or whatever you can do. And if you have any problem, let me know. Normally I do that one.
Okay. Okay.
Okay, so I'll stop.
Okay. Thank you, sir.
Okay, bye.
Thank you, sir.